Hello everybody. Today we're going to talk about the three-phase balancing system, the circuit analysis of this. Last lecture we talked about the what is the three-phase balance system and what is the positive sequence, negative sequence, and line voltage, the phase voltage, or line to neutral or line to line voltage, all these basic concepts. So today we're going to look at the simple techniques to analyze the three-phase circuits. And that's not really much different from the circuit analysis of a single-phase circuit, because the three-phase, if you remember last lecture, we introduced the we calculated the neutral the current on the neutral line, right? The neutral current actually is 0 for three-phase balance system. That is true for all three-phase balance system. So therefore, we can kind of if the three-phase circuit does not have the neutral line already, we could add the neutral line, so we can single out one phase out of the circuit. So we call the per phase equivalent circuit, and so we can solve that very similar to the single phase circuit analysis, except that if you ask about the three-phase power, make sure you multiply by 3, because each phase the load impedance is the same, and they will absorb the same amount of complex power, right? And the second topic, I want to talk about the Y-connection and delta connection, because sometimes the load is delta connected, and it will much more simple if you can convert that to the Y-connection. And in the practical world also, there's the practical example of why we use Y-connection, some why use delta connection. And we're going to introduce that as we go to the two topics. So we're going to have 2 video clips today, and as always, I'm going to put the Google Colab notes in the description down below, and check those Google Colab notes for the details. Okay, so for the three-phase balance circuit, I'm going to illustrate this with an example. Let's see, we have a three-phase balance circuit. Remember what the three-phase balance circuit? That means the source, they have the same magnitude or amplitude. The amplitude in time domain, the magnitude in phasor, and their phase angles are displaced by 120 degrees. Depending on the sequence, it could be positive sequence or negative sequence. The positive sequence means the B phase is lagging A phase by 120 degrees, and the C phase is lagging B phase by 120 degrees, right? So if you look at the phasor on the complex plane, so you go from the phasor for A phase and then go to the phasor for B phase. So you're gonna go the clockwise direction. That's the positive sequence. The negative sequence is basically if you flip any of these two phasors position, and then you get a negative sequence. And then from an A phasor to B phasor to C phasor, you're going to have the counterclockwise direction. That means the B phase is leading A phase by 120 degrees, and the C phase is leading B phase by 120 degrees. Okay, so that's for the source. For the load impedance must be the same, right? Or if you have a line impedance, and those line impedance for each phase would be the same. So if the system both has the same impedance in each phase and the voltage they are displaced by 120 with the same magnitude, that form a balanced three-phase circuit, right? And here we're given the positive sequence. That means the B phase lagging A phase by 120. So if you know one of these voltage source voltages, let's see here we give the phase to neutral phase voltage or line to neutral voltage for the A phase, V sub AN, that's 277 with 0 phase angle. That means we also know the phase angle, the VBN and VCN, because they have the same magnitude, and the phase angle will be displayed by 120 degrees. And that means, so this is implicitly given for VBN is going to be equal to 277 negative 120 degrees, and VCN is going to be 277. So that's further lagging by 120 from B. That means negative 240. And typically we don't see the phase angles you go more than 180, the absolute value. So we will add another 360. So negative 240 plus 360, that you got a plus 120 degrees. If you plot this phasor, the VCN, either using negative 240 degrees or positive 120 degrees, you're going to get the same location on the complex plane. Right? That's just a sort of a convention. We don't really go, the phase angle go more than 180 degrees. The question asking is the line currents. We calculate the line currents and then find the complex power delivered to the three-phase load. So that means the power delivered to all three-phase impedances, right? So therefore, we can calculate this quite straightforward. Remember, since this one does not have the neutral line, so one comment here is we normally don't use the mesh current. So let's see, if you do the mesh current trying to find the current IA, IB, IC, normally you don't need that because we know this. We're going to utilize the property of three-phase balanced, and the neutral line is going to be zero current. So I could add another neutral line here. So therefore, that will not change the circuit. That means that will not disturb the circuit. The circuit will not feel anything. And so the IA, IB, IC, because this neutral line has zero current, right? That means these two neutral points, the source neutral and the load neutral point have the same potential, right? The voltage difference is zero. So I could just single out this one phase. So let's see, I can just look at the single phase, and then this is ZL. So this is Z sub L, this is Z sub line, and this is V sub AN. And I could just, instead of solving the three-phase circuit, I look at the same single-phase circuit because this is a neutral line, right? I can single this out. So therefore, the IA is going to be equal to VAN divided by Z line plus Z sub L, right? So if you plug in the numbers, so this again here, the complex number calculations, I hope everybody by now you're very comfortable doing this number crunching. So I did the number crunching beforehand using the Google Colab, using the little Python code. So I have the solution that's equal to 23.73. The phase angle for this is going to be negative 64.1 degrees. So that will save some time. Of course, this is going to be ampere in RMS value. So because the voltage in RMS value, right? So once I figure out the IA, so this is for the first step. Once I figure out the IA, I don't need to calculate IB, IC, and IC. I just use the property of the positive sequence because IB, I know that IB is going to be lagging IA by 120 degrees. So therefore, with the same magnitude, and IB is going to be equal to the IA times the E2J more 120 degrees. So that's going to be equal 23.73 negative 64.1 degrees minus 120. Here again, we are going more than 180, right? So we just add another 360. So what I do, I just add another 360 to bring that. It's not critical, but it's sort of convention. We don't go 0.1 minus 120 plus 360, or you can see add 240. So therefore, I get the angle is 175.9 degrees. And again, here this RMS value. And so therefore, for IC, I can go just IA times E2J 120 degrees. and that's going to be equal to 223.73 negative 6.64.1 plus 120. So this will be within 180 degrees, so we don't need to do anything to bring it back. And so therefore the phase angle, that's 55.9 degrees, and RMS value. And so this is the, again here, this approach will have the risk of carrying over the error you may have with I8, right? So if you don't want to risk that, and you could alternatively calculate the IB just like you did with so that would be VBN divided by Z line plus Z sub L. So by doing this, you will get the same answer, right? So the VBN, that's going to be equal to because the positive sequence, the VBN is going to have the same magnitude but has negative 120 degrees, and you add the Z line. So you have Z line is 0.1 plus 0.5 J, right? And the Z sub L is, let's see the numbers. That's the 5 plus 10 J. Right, so you can calculate this, and so you will get the same answer. So in this way, if you find the B phase have a different magnitude from the A phase, then you will find you made an error either in IB calculation or IA calculation, right? So that's the alternative way of kind of doing the cross section, the cross check. And which is very important if you do during the exam, or if you work on something independently and you don't have somebody else to check for you, you can check yourself, saying I use an alternative approach. I can check whether the solution I get is correct. So, and then the three-phase power actually is simple. The three-phase power delivered to the load. Remember, one way we can calculate the power is using the current, the magnitude square times the impedance. And now since we have three phases, we just need to multiply by 3. And if I do that, the answer is 8.45 plus 16.89 J. This is complex power, of course. So this impedance, because this, you see the Z sub L has the real part and imaginary part. Imaginary part is in positive, that means Z sub L is inductive, so therefore also absorb the positive reactive power, which is 16.89. This the unit for this kVA, and so the real power is absorbed by the load impedance, three-phase load impedance more than 8 kilowatts, and the reactive power absorbed by the load impedance more than 16 kilovars. Okay, so that's the example of doing the calculations. Alternatively, if you want to really verify that, alternatively, you could calculate the you could calculate the voltage across these, right? So if you can calculate, let's say V A sub L, right? Let's see, this VA phase. You can also calculate the V sub L. So that's alternative way. That, I think that's the more complicated. Again, here if you use the line current, you calculate. If you made a mistake, that you're going to carry over to your three phase, right? So alternatively, you can calculate V sub L using the voltage division, right? So V sub AL is going to be equal the Z sub L divided by Z line plus Z sub L times V sub AN. You calculate these, and then you can calculate the three phase. That should be equal to 3 times the VAL square divided by Z sub L conjugate. That's another way of calculating this, right? Remember, we have 3 ways of calculating complex power. We can use voltage times the current conjugate. That's for a single phase. For 3 phase, you multiply by 3. And then the another one is use the current, just as we did, current magnitude times Z times the impedance, or you can use the voltage magnitude square divided by the impedance, the conjugate. The reason for the conjugate because the I is equal to V over Z, right? So the I conjugate is going to be equal V conjugate over Z conjugate. That's where this Z conjugate is coming from for using the voltage magnitude. So this should give you the same answer. That's another way of doing the cross-checking. Okay, so that's the video is a little bit long, but that's how we do the three-phase circuit analysis. Next, we're going to look at the Y and delta connection. See you in a moment.